In the first lecture, we looked at the question of how to find the slope of the tangent line to y equals x squared at the point 1, 1. And as you recall, what we did is we found a point on the curve y equals x squared with coordinates x, x squared. We drew a line between those 2 points, which we called the secant line. We calculated its slope, delta y over delta x, where delta y was x squared minus 1, and delta x was x minus 1. And we wrote this expression that said the lim, as x goes to 1 of x squared minus 1 over x minus 1, is the slope of the tangent. Now, we explored what that meant, and along the way discovered that the answer here is 2, but we want to do this more generally. So now our function is y equals f of x. Our point is no longer 1, 1, but is at x equals a, so this point is a f of a. We pick a point on the curve x f of x, draw a secant line, and calculate the slope as delta y over delta x. This time, however, delta x is x minus a, and delta y is f of x minus f of a. The ratio is the slope of our secant line, and then we want to take the limit of that, and that'll give us the slope of the tangent. The derivative of f of x at x equals a is this limit. Okay, so this is the definition of the derivative. Notation here is f prime of a, and that means calculate this limit. If that limit exists, it's the slope of the tangent line to y equals f of x at x equals a. So here's our definition of f prime of a, and now let's see how it can be used to calculate slopes of tangents for specific functions. So our first example, f of x is going to be x squared plus x, and we want to calculate f prime of 2. Now, according to our definition here, it's going to be the limit as x goes to 2 of f of x minus f of 2, because a is 2, over x minus 2. We plug in f of x is x squared plus x. F of 2 is 2 squared plus 2, or 6, over x minus 2. Now, if you look, you discover that when x equals 2, the top is 0, and so is the bottom. So this is a 0 over 0 indeterminate form. We know that we have to do some work to find this limit, and the work in this particular case is going to be factoring. And x squared plus x minus 6 factors as x minus 2 times x plus 3, all divided by x minus 2. And now when we stare at this limit, we see this x minus 2 over x minus 2, and that's going to give us a 1. The x plus 3 is going to give us a 2 plus 3, or a 5. So when we do this calculation, we get 1 times 5, or 5, and that's f prime of 2, which is the slope of the tangent to this curve at x equals 2. This definition is not the definition that we will use most of the time. So I want to show you a second definition that's equivalent to this one, but is in certain cases easier to use. So we start looking at our picture again. We have our point A, f of a, where we want to draw a tangent line. We pick another point on the curve y equals f of x. We draw a secant line through it. The slope of our secant line is going to be delta y over delta x. To find the slope of the tangent, we're going to take this point and slide it down the curve towards af of a. And what's going to happen then is delta x is going to go to 0, which means the slope is going to go to f prime of a. And we're now writing that as the limit as delta x goes to 0 of delta y over delta x. Here's your slope. As we slide this point down, delta x goes to 0. That's going to be the slope of the tangent, or our derivative. Now, however, we're going to calculate delta x and delta y a little differently. This time, we're going to call delta x equals h. Okay, so h is this length right here. And the way this is drawn, this is positive. Had we gone the other direction, h would be negative. If this is h, and that x-coordinate is a, this x-coordinate is going to be a plus h, and the function value there is going to be f of a plus h, which means that delta y is going to be f of a plus h minus f of a. And that's what we write in here for delta y. Delta x is just h. We take the lim as h goes to 0 of this, and that's f prime of a. And that's our second definition of the derivative, and it's the version that we'll use most often. Let's calculate some derivatives using this new definition. So what we're going to now do is look at the function f of x equals x squared plus x and calculate f prime of 2. This should look familiar because we just did this calculation with definition 1, but we want to see how things work if we use this second definition. So f prime of 2 is the lim as h goes to 0 of f of 2 plus h minus f of 2 over h. A is 2 here. And what we do is we plug 2 plus h into f of x, and we get 2 plus h squared plus 2 plus h here for f of 2 plus h. And as before, f of 2 is 6. Now we square 2 plus h, and we get 4 plus 4h plus h squared plus 2 plus h minus 6 over h. Now we want to simplify the top, and what we notice here is 4 plus 2 minus 6 is 0. 4h plus h is 5h. So the whole top ends up being just 5h plus h squared. The bottom is h. We notice that an h factors out of the top, and we can write this thing as the lim as h goes to 0 of h over h times 5 plus h. Now h over h is going to give us 1, and 5 plus h is going to go to 5 plus 0, or 5. So we get 1 times 5, which is 5, which is what we got last time. In these sorts of problems, what we're looking for when we do these calculations is to get a term that looks like h over h, and then what's left over we should be able to take the limit of easily. Another example. Here f of x is 1 over x, and we want to calculate f prime of 2. So our definition says that f prime of 2 is going to be the limit of f of 2 plus h minus f of 2 over h. This should look familiar. Now, here, however, we're plugging 2 plus h and 2 into our function 1 over x. So what we're going to get is 1 over 2 plus h for f of 2 plus h, 1 over 2 for f of 2 over h. And when you put h equals 0 in here, you get 1/2 minus 1/2, or 0 in the top, 0 in the bottom, 0 over 0 indeterminate form. This is what happens to you when you use these methods to calculate derivatives. So we're going to have to do something to figure out what 0 over 0 is. Factoring is not an option here, but what is an option is we have fractions in the top. We can combine them, but to do that, we're going to need a common denominator. And the common denominator is going to be 2 times 2 plus h. So this first term becomes 2 over 2 times 2 plus h. This second term becomes 2 plus h over 2 times 2 plus h. we subtract the 2, and 2 minus 2 plus h is minus h. This denominator is 2 over 2 plus h, and everything is still over h. Now remember that dividing by h is the same as multiplying by 1 over h. So this h here has become this 1 over h. This term is what we had here. And now if you look at this thing, there are our h's. So we're going to regroup it. So we've got our h over h. What's left over is this term. That's going to give us a 1. Now what's this going to do? Well, the top is going to look like minus 1, and the bottom is going to look like 2 times 2 plus 0, or 2 times 2. So this whole mess is going to look like minus a quarter. And our limit is minus a quarter times 1, or minus a quarter. Let's look at the following graph, which gives the population of Morania in terms of the year. So what we can see here is at the beginning of 1970, there were 1.5 million people in Morania. That's what this point 1970, 1.5 means. Now you'll see this red line is a tangent line. And suppose we know that that slope is 0.05. What are its units? Well, if we look at units of slope, we can see that it's going to be a delta P over a delta T. And P is population, which is in millions of people. Delta T is units of years. So what we're going to get is the units of P prime of 1970 are millions of people per year. So another way to say that is when T equals 1970, the population of Morania was growing at a rate of 0.05 million people per year. Okay, now let's look not at the slope of the tangent. Let's write down the equation of the tangent. And we're going to use the point slope formula. Y minus y naught equals mx minus x naught. M is the slope of the tangent line. X naught, y naught is our point of tangency. Now in this particular case, the independent variable is t. The dependent variable is p. So this thing translates to p minus p naught equals mt minus t naught. Now m is our slope, which is given by the derivative, and t naught, p naught is our point of tangency. So what we're going to get is the following equation. P minus 1.5 is equal to 0.05 t minus 1970. Now let's return to our discussion of position and velocity. Here what we have is the graph of the position of an object. S is in meters. S is going to be its position relative to the origin. This thing starts 7 meters to the right of the origin at time 0. Okay, we can see that in this period it heads back closer to the origin because we're down here to maybe 1.5, and then we move away from the origin again. Now let's look at the slope of the tangent here, and this is the tangent when t equals 2. Our slope is going to be delta s over delta t, and that's in meters. T is in seconds. The units here are meters per second. That's a velocity, and in fact, the velocity at A is s prime of A, the derivative of there, and it's in meters per second. Now, let's see what the velocity tells us. Well, at t equals 1, we can see that the slope of our tangent is negative, which means our velocity is negative, and that means that we're headed in the negative direction back towards the origin. At t equals 2, our slope is positive, so we're headed away from the origin again. At t equals 3, the slope has become larger, and in fact, this is about as big as the slope is going to get, so this is as fast as our object is going to move, and then at t equals 4, we can see that it's slowing down again.